Hello. Hi, folks. Hi. Oh my gosh. Bang Bang Con. So excited to be back. Well, I am so glad Piet has already come up a couple of times at the conference. I hope everybody is just as excited as I am to talk about Piet today. I'm Anjana Vakil. You can find me at Anjana Vakil on Twitter. And I'm really stoked to talk about Piet. Uh, so let's dive in. The slides are up on Observable, where I work as a developer advocate. And I am really stoked that I think a lot of people already are familiar with Piet, but I hope for the folks that are new that this will be illuminating. So, um, Piet Mondrian might be a name that you recognize, but if you don't recognize the name, I'm pretty sure you recognize his art. So he was a Dutch painter famous for doing these very striking compositions, abstract paintings with large color blocks and lots of white space. And the question that we as intrepid programmers might be asking ourselves is, cool, art is nice, but what if we could run a piece of art like this as a program? Uh, so this is exactly the question that David Morgan Marr posed when he invented the programming language called Piet, named after Piet Mondrian. So Piet is an esoteric programming language, or esolang, depending how you pronounce it. I think a lot of folks are familiar with esolangs, but in case you're not, that's essentially a language that's not intended for practical programming and getting work done, but rather for joy and excitement and exploration and learning, and in many cases pushing the boundaries of our notions of computing and what programming even is. And so this is definitely the case for the language Piet, where we are going to treat abstract art as the source code for programs. What does that even mean? What does a program look like in Piet? Well, here are some examples. All of these are different ways that you can code a world program in Piet. So all of these programs print the output "Hello World" to standard out, and this animated one has three different versions of ways you can color this program. So as you can see, they're all very colorful. They're made up of blocks of bright colors, and we're going to see how we can execute images like this as code thanks to the Piet interpreter. So how does Piet interpret these these pixel art pictures as programs? Well, it's all about colors. So as we saw, Piet programs are made up of bright colors, and this is the set of colors that can go into a Piet program. So we have the kind of rainbow colors, 6 rainbow colors here, a lighter version and darker version of each, and then white and black, which are kind of special colors, which we'll talk about in a moment. And so the idea is that in a Piet program, and here we've got a very simple little 10 by 10 pixel blown up program here. In a program, the blocks of a contiguous group of pixels of the same color represent a piece of data, so an integer value. And that is going to be the number of pixels making up that block. So in this case, we've got a magenta block here, and you'll notice it has some holes in it. There's some black areas and other colors inside of it, but all of these pixels make up a contiguous area that has 33 pixels. So this is going to be a magenta block of value 33. And then we have a dark magenta one here, which has 11 pixels, so 10 here and then one more. There's also a couple more 1 pixel blocks of dark magenta there, and so on and so forth for the different colors. Now, keep in mind, this is all about the contiguous series of blocks of pixels. So, for example, here we have 2 different dark cyan blocks, one that has value 5 and one that has value 1. They're separated by this white. Now, as I said, white and black are kind of special colors. White is essentially like a void. It's like a filler. It's kind of empty space. And we're going to see what that means in a moment. And then black is essentially like a stop. It's also not a value, but it's more like the edge of the image. So essentially, it's a no-go zone. We'll see what that means in a moment. All right, so the way a Piet program is interpreted is thanks to the help of something called a direction pointer. The way the direction pointer works is when we start execution of a program, the direction pointer starts out in the top left pixel of the image, and it starts out pointing right. And what it does is, if it's in a color block area, it's going to try to move to the edge of that colored area, that same colored block, that is in the direction that it's pointing. So in this case, to the right. So here it's going to move from the top left corner 5 pixels over, or to the 5th pixel over. And this is the rightmost edge of this magenta block. Then it's going to try to move on from there into the next block, in this case, into this dark magenta one, and so on and so forth. Now here, I don't need to move to the edge of the dark magenta block that I'm in because it's only 1 pixel wide. So I'm already at the edge. So I can go into the dark cyan, go into the next one, eventually the green, and so on until I reach this light yellow block. Now here, the furthest edge in the direction the pointer is pointing is actually not here, but further down the image. It's going to be this lower rightmost pixel here. That's the furthest edge in the direction of pointing. So we jump down there. And now we've reached the edge of the image. So we can't go anywhere else, can't move on. So what the pointer does in that case is it turns 90 degrees clockwise. So it's going to start pointing down. And then it's going to move. Sorry, we just jumped ahead a little bit. It's going to move to the edge that's furthest in the down direction. It hits the edge again of the image. So it has to rotate once more. It's going to move again to the furthest edge. Now it's pointing left. So it's going to move that way, which is this block over here. Now it's run into black, which, as we said, operates sort of like the edge of an image. So it can't pass through the black area. It has to turn again and move to the next, the edge in the new direction, which is now up. So it's going to move back up to this top pixel here, which again is the edge of the image. It can't move on from there. So it turns again, but at this point it has done a full rotation in this light yellow block, and it hasn't been able to get out. So it's stuck. And that is how we tell a Piet program to stop executing. So this means the program is over and execution is finished. Now, we didn't look at this one, but the white pixels essentially are sort of empty space. So the pointer moves unhindered through any white pixels. Okay, so now how do we take this pointer movement and turn it into doing something? Well, it turns out that changes between one block of color and the next block of color, changes between those colors are actually corresponding to commands to the Piet interpreter. So the colors are arranged in 2 cycles. On the one hand, we have a hue cycle, which moves through the rainbow colors from red, yellow, green, cyan, blue to magenta, and then back to red, and goes on in that cycle. And this is called the hue cycle. We also have the lighter and darker versions of each color, and that makes up another cycle called the lightness cycle, where we go from light to normal to dark and back to light. So if we're, let's say, moving out of a light red block and moving into a dark magenta block, that difference in colors is going to represent 5 steps in the hue cycle and 2 steps in the light cycle. And the way that these steps work is the number of hue and lightness steps for a given color change corresponds to a command that the interpreter is going to run to actually do something. So in this case, if I were to go from light red to dark magenta, that's going to correspond to the out car command. And we're going to see what that means in a second. And keep in mind that these are not absolute, the color, like each color does not correspond to a particular command, but rather the difference between them is what creates a command. So if the color changes, if now I'm in a dark magenta block, then moving to the light red color would be a subtract command, or moving 1 step in the lightness cycle to light magenta would be a push, and 2 steps in the lightness cycle to regular magenta would be a pop. Okay, so moving fast through all of this, but we're not going to have time to look at all of these commands, but what do these commands do? Let's take a look at a couple. What they do is they tell the interpreter how to manipulate values on a stack. So a Piet program, it runs by means of a stack which has integer values onto it. And each command gives the program something to do with that stack. So for example, the push command says, okay, take the value, the number of pixels in the block of color that you just exited in that previous block, and push that value onto the stack. Then we have a pop command that says, take whatever's on top of the stack and throw it out, take it off and throw it away. There are some commands like add, which assumes that there are at least 2 values on the stack and says, take the top 2 values, remove them, add them together, and then push the sum as a new value onto the stack. There are also some more commands that have various operations, like duplicate, for example, is one where we read the top value on the stack, and then we push another copy of it to the top of the stack. We can also do input and output. So we can read from standard in with the in commands, and with out commands, we can take the top value on the stack and print it to standard out, interpreting it either as a number, because everything on the stack is going to be integer numbers, or we can take that integer and interpret it as a character code and print the character that it represents instead of the number. So you can check out the references in the slides for a link to David Morgenmar's description of all of these commands. Okay, so let's see how this works and try to run a program. Okay, so we have our little image here, our 10 by 10 image, and we know how our color commands work now, and we know how our pointer works. So let's put it all together. Okay, when I start execution, the pointer starts out in the top left, as we saw before. It's in the magenta block, which has a value of 33. It moves to the edge of that magenta block, so it's still in the same block, this magenta 33. Then, as we saw, it moves into the dark magenta. Now, that difference from the previous colored magenta to dark magenta, that's a lightness step of 1 and 0 steps in the hue cycle. That corresponds to the push command. So it takes the previous value, this 33, and pushes it onto the stack. So now we have something on our stack. Started out as empty. Okay, we keep moving into dark cyan. So now the difference between the dark magenta that we were in before and the dark cyan that we're in now corresponds to that duplicate command. So what we've done is we've taken the previous topmost value, which was that 33, and created a new copy, put it on the stack. So now we have two 33s on our stack. Then we're going to move into this green, where the difference between dark cyan and green, even though all these colors look totally different, the number of steps is going to be what corresponds to the next command we're going to do, and that is out as a character. So now what we've done, and let's just go back to see here, well, we took the topmost value, and when we moved into that green, that out command told us to print it as a character to standard out. And guess what character it made? An exclamation point. Oh my gosh, how unpredictable. And then we move into this light yellow, and that difference is actually going to be the same difference as we saw from dark cyan into green. So we get that same out command, and we print that last 33 that we had there as another exclamation point. Now we're in our light yellow block again, and we saw how that goes. We try to move, we have to turn, we try to move, we have to turn, and so on and so forth, until we realize that we're stuck. We've retraced our steps, gone in a complete circle in this same block, and we can't get out. So we exit the program, and we are done. Bang, bang. So, oh my gosh, we did it. We saw Piet run. Now, this was a really simple program, but you can do anything in Piet that you can do with a computer. You could write an interpreter for an entirely different esolang, for example, which Matthias Ernst did when he wrote a brainfuck interpreter in Piet. Like, oh my gosh. You could even Sergey Luis developed an assembler to basically like compile to Piet and can create even more complex programs that way. This, what we're looking at, and it's very small here, but this is a text adventure game written in Piet. Amazing. So I think this is just like so cool that you can really force your mind to expand in terms of the notion of what is a program, what could execution be, how could the act of programming be more like the art of programming. And I just think that Piet is just such a great example of like bringing joy and excitement to programming. And so I am really happy that everyone has been excited about it. Thank you all for listening, and I have some resources for y'all in these slides, which you can find on observablehq.com/@Anjana/Piet -BangBangCon. So yeah, go check out the resources listed here to learn more about all of the details of Piet and see some other really awesome programs. There are some really great online tools, and interpreters, including an amazing web IDE called Master Piet that Ricoeur Center alumna Gabrielle Sincadieu made, which you can play around and make Piet programs and try them out with an interactive debugger. So go forth, play with Piet, enjoy, and I hope it brings you lots of excitement, surprise, and joy. Thank you.